All right, welcome to Chapter 5. You have made it a long way. This officially, Chapter 5, is the beginning of the mid-chapter, right? So halfway through. It's a lot of information we're learning, and you're doing a really great job. This chapter, we're going to introduce to you your very first chemical reaction. Your very first chemical reaction. Or your very first kind of chemical reaction, okay? Chemistry happens in lots of different ways, all over the place. And chemistry occurs when two entities, be it molecules or elements or whatever they are, come in contact. They have to come in contact with each other. And that's a general principle of nature, right? Things come in contact when they rearrange or share electrons or whatever it is. Sodium won't give an electron to chlorine until they're close enough for that to occur. So a chemical reaction, things need to come in contact. Now, if I have a pile of stuff, here it is, ready? Here's my pile of stuff. There's chemical A. And here's another pile of stuff. It's chemical B. And I'm hoping that I can get A and B to react to form something new, all right? And if this is solid and this is solid, right, it's going to be hard to mix A and B. I mean, I can put them in the same container and I can stir them up and stir them up fast or something like that. But at the atomic level or the molecular level where those molecules actually are, if this is a solid, that means it's chunks of material, and most of the atoms inside or most of the molecules inside won't come in contact with the other chemical. So chemistry cannot occur very well if things don't come in contact. It doesn't occur at all if things don't come in contact. And if the bulk of the material can't come in contact with each other, then you can't have anything happen. Okay? Now, to facilitate this, what we often do is, instead of taking a chemical like A and B and trying to mix them as solids, what we'll do is we'll put A into some water. So if I have some water and I put A into it, then A dissolves in the water. And I think you've seen probably a cup of sugar and you put it into water and stir it up, and it's like the sugar's gone. Right? What happened to it? What happened to it? Well, all the water molecules surrounded the sugar and separated them up so that now they can all be individual molecules. And so if I put A into water and dissolve it, and then so now I have some A in here, so it's going to be, the chemical reaction is now aqueous. What does that AQ mean? Do you remember?
It's an acid.
No, it means it's dissolved in water. A is dissolved in water. So remember, the S stands for what?
Solid.
L stands for?
Liquid.
And G?
Gas.
Gas. And AQ, which is aqueous, that means what?
Water.
It means
Dissolved
it's dissolved in water. Very good. So I do the same thing with my B. It's now B aqueous, and then I can combine those, and when I combine those two mixtures of the chemicals dissolved in water, A and B can roam around. They're free to move, and molecularly, meaning each at their own single molecule level, they can find each other. They can find each other and react. All right? So that means that for chemistry to occur, chemistry occurs much easier if we have things in aqueous solutions. So our first kind of chemical reaction that we're going to introduce to you, it has the molecules, or the chemicals, dissolved in water. And that's what this says here. Reactions in aqueous solutions. To understand this, we have to have a little vocabulary, okay? If I have my water here, here's the water, and here's my pile of A, all right? if I take the A and put it into the water, right? Let's say I'm doing a little bit of kind of chemistry here, just mixing these solutions. Now I have A in solution, we call it, solution. A goes into water, and now I have A in solution. And this is the solution. Solution. Now, it doesn't mean like the answer to the problem. The word solution also means when you take something and put it into a liquid and form a mixture of that chemical dissolved in that liquid. All right? That's called a solution. The liquid that you use to make the solution is called the solvent. The solvent. And the thing that you put into the solvent is called the solute. So this is solvent, and this is called solute. All right? Solvent, solute, solution. All right? Now, sometimes you take something like water and mix it with another chemical that is also a liquid, like ethanol. Ethanol. And if I mix these two together and then I get a solution of these two different liquids and they mix together so I can't see a separation. If this was oil and this was water, you'd mix them together and you would get a heterogeneous mixture, right? The oil would float on top. But when you mix ethanol and water together, you get a solution, okay? And so in this sort of thing, we might say, okay, well, where's the solvent and where's the solute? And it's kind of hard to tell. So we define the solvent as the chemical that is in the highest concentration. And that essentially, concentration means the amount, the ratio of solute. Now, what's the solute again?
The thing going into the water.
That's right. It's so the concentration is the ratio of solute to solvent. What's the solvent?
The water.
Right. Or the liquid that's doing the dissolving, right? Because sometimes it's not water. I mean, in this class, it's almost always water. But moving forward, we can recognize that it can be other things as well. Okay, very good. We have two new words like dilute. Dilute. Now, you've probably heard that word. Have you heard the word dilute before?
No.
Okay, dilute means that, or dilute, another way to say it, is that the solute is very, very, very small amount compared to the solvent. So in the solution, you just have a little bit. Like here, see, I just put a little bit of salt in. We could say that solution is dilute. I could put more and more in, and see how I put it in, and the material dissolves. It separates. I could put more and more and more in until at some point, the water won't be able to dissolve anymore. And when the water can't dissolve anymore, then what happens is the stuff just starts to pile up at the bottom, right? Have you ever put so much sugar into either maybe you put a lot of cocoa mix, chocolate milk mix into water or milk and then stirred it up, and the result is a big pile of chocolate milk on the bottom? Have you ever done that?
Yeah.
In the olden days, cereal tasted gross, and so we would have to put sugar on top of the cereal every morning. And it was a big fight with the parents because the parents would say, you don't need that much sugar. You don't need sugar. Don't put sugar on your cereal. But we would have to sneak it or whatever we could do. And then in the end, the sugar was always on the bottom, a pile of sugar on the bottom. And it was, it was way too sweet, the little bottom. But, that's where I learned about solutions that were concentrated. Concentrated means there's more solute than can be dissolved. The water dissolved a lot of the solute, but it couldn't dissolve it all. And so there was a pile of stuff at the bottom, right? And that's what the term concentrated means. And what's the other term? Did you catch that? When there's just a little bit?
Dilute.
That's right, dilute. Very good. Okay, so we also have a term that we need to make sure we understand when we talk about it, and the term is solubility. Solubility. Solubility refers to how much of the solute can actually dissolve in the solution. Okay? And this is a big deal because some solute doesn't dissolve in water, right? For example, you know that if you take dirt and put it into water, the dirt just doesn't disappear like the sugar seems to disappear. The sugar in water, it'll all disappear. But if you put dirt or if you put flour, a little teaspoon of flour into water, the flour doesn't dissolve. It doesn't dissolve. So we say that the flour or the dirt is insoluble. It's not soluble. Okay? The sugar is soluble. The salt, sodium chloride, like salt from the salt shaker, we know about that. It dissolves in water. Okay? But we also know that there's a limit to the solubility of sugar and salt. If you put too much in, a lot will dissolve, but eventually the solubility limit will be reached. Okay? And we have another word that we can use when we say we've put as much solute in this solution as we can. That means the solution is saturated. Saturated. We can't put any more solute in here. If you have a saturated solution and you put a little bit more in, what's going to happen to that little bit more?
It's not going to dissolve.
It's not going to dissolve. Just going to make a little mountain on the bottom, right? All right. So solubility tells us how much material, solute, can dissolve in the solvent. Unsaturated solution means that, yeah, you can put a little bit more in. So there's a little bit more material that can dissolve in that amount of water. There's an interesting word called supersaturated. We don't talk much about it, but I'm going to show you kind of an interesting situation because you can create conditions where solutions are dissolving more solute than they theoretically should be able to. So if we say, oh, you can dissolve 15 grams of salt into water. But if you raise the temperature of water, you can dissolve more. So if you raise the temperature of water and then put in maybe 20 grams of salt and it all dissolves, if you slowly lower the temperature, the salt will be tricked into staying in solution. And we call that a supersaturated condition. Okay? All right. Now, on the back of our periodic table, we have so many goodies. And this is one of the little tables that we have. It's called the solubility table. The solubility table. Can you find it on the back of your periodic table?
Found it.
All right. These are rules that help us know whether or not a compound will be soluble in water. All right. And number one, for example, says all the compounds of alkali metals. That's group 1, right, on our periodic table. So that's this group. So all compounds that contain lithium, sodium, potassium, rubidium, cesium, all of those compounds are soluble in water because that's what the solubility rule there tells me. The second rule, all salts containing these polyatomic ions, the ammonium ion, the nitrate ion, the perchlorate ion, the chlorate ion, and the acetate ion are soluble. That's rule number 2. Okay, so there's a handful of rules here, and I won't give them all away. I'll let you read through them gradually over time. And then there's 2 rules down here also that are about insoluble compounds. All metal hydroxides So that's a compound that contains a metal, right? And we know our metals are on the left side of that staircase. And the hydroxide ion, OH minus, or the oxide, O2 minus. All metals that contain oxide and hydroxide are insoluble. What does insoluble mean again?
It means that it's not soluble.
Very good. Does not do what?
Does not dissolve in water.
That's right. Very good. Excellent. Insoluble means it does not dissolve in water. So all metals that have hydroxides or metals that have oxides are insoluble except, and so see how some of these rules have excepts in them, except those of group 1A and those of calcium, strontium, and barium. All right. So these rules are kind of interesting, kind of complex, and so we want to, like the polyatomic ion chart, use this chart over and over and over anytime we have a question about solubility. And as we do that, then gradually we'll begin to learn the rules. Okay? Now, let's use that chart to try to find out which of the following compounds, or if these compounds are expected to be soluble in water. Okay? So I'll bring the chart up here, and you can look on yours if you want to, or you can look here on the computer, on the screen. But the first one, what is the name of this compound here? Do you know? Ca is element 20.
Calcium carbonate.
Very good. Calcium carbonate. Now let's see if we can use these rules to find out whether calcium carbonate is soluble or whether it's insoluble. All right? Let's see. What rules can we find? Look through these rules and see if you can find anything about calcium or anything about the carbonate.
Oh, carbonate.
What's it say? Rule 6?
Yeah.
Read it for us.
It all states
Salts.
that,
All salts.
All salts that contain phosphate, carbonate,
That one's the sulfite.
sulfite.
And sulfide.
Sulfide are insoluble. So that's
Insoluble. Wait, there's an except.
except those of group 1A and NH.
So this is group 1A right here. Is calcium in group 1A?
No, it's in group 2A.
Yeah, that's right. It's in group 2A. Very good. All right. So, anything that contains carbonate is insoluble unless it has something from group 1A or ammonium ion. So that means that one is no, it is not soluble in water. Okay, very good. How about the next one? What's the name of that compound, first of all?
CL.
What do you think about this? Come on.
Is it iron chloride?
That's right, it's iron chloride. Now, iron is a transition metal, so I do have to put a number in between the iron and the chloride, right? What number should I put in there?
2.
Why did you decide on the 2?
One iron equals 3 chloride.
Okay, very good. So I know that I have an iron ion and 3 chloride ions necessary for that iron ion. Do I know anything about the charges of any of these? Chloride is element 17, right?
Oh. Yeah, it wants one more.
So these are all -1. So what does that mean the iron must be?
Positive
Positive 3. And that's the number we put in there to tell people what that iron is. So this is not iron 2 chloride, but it's iron 3 chloride. Okay? Did you understand that?
Yeah.
Okay, wonderful.
Yeah.
Now let's find out if it's soluble or if it's insoluble.
Oh, number 3.
What's it say?
All chlorides, bromides, and
Iodides. Good.
Iodides, salts containing chlorine, bromide, or
Iodides, ions, yeah.
are soluble except when combined with
Silver.
Ag, silver,
Pb is lead,
lead,
and Hg is mercury.
mercury.
Okay, so what does that mean? Is FeCl3 iron 3 chloride soluble or insoluble? Yes,
Soluble.
that's right. It's soluble. It dissolves in water. Wonderful job. All right, let's name the last compound and find out whether it's soluble or insoluble.
Number 3 again.
Okay, number 3 again, but let's name it really quick first. What's its name?
Lead
Very
chloride.
good. And lead 2 chloride, because the lead ion has a +2 charge, because each chloride ion has a -1 charge. Very good. Lead 2 chloride. And what did you decide? Yes, soluble, or no, insoluble?
No.
Okay, what rule?
3.
Rule 3. Chlorides are generally soluble, except there are some exceptions, and lead is one of them. Fabulous job. Very good. So you're learning how to use this solubility table to know whether or not different compounds dissolve in water. Fabulous job. Fabulous work. Yeah. So here's the question. Now, this question doesn't have to do with our solubility table, so I'll move that solubility table out of the way for now. But this question is asking about the solubility of a given, or how much of a given solution the material will actually dissolve. So the question says, the solubility of sodium chloride, and that means how much sodium chloride can be dissolved in water, is 39 grams of sodium chloride for every 100 grams of water at 100 degrees Celsius. Now remember, I said that temperature is important, and that's, I don't know if you've ever made your own homemade syrup, but the recipe for homemade syrup is 2 cups of sugar for 1 cup of water. 2 cups of sugar doesn't dissolve in 1 cup of water. So how are you going to do that? You have to heat it up, and when you heat it up, then you get some changes that allow the whole solution to become, or the whole system to become solubilized, and an aqueous solution. So in this case, we're at 100 degrees, and we know that at 100 degrees we can put 39 grams of salt into 100 grams of water. And we want to know, if I put 10 grams of salt in 50 grams of water at the same temperature, is the resulting solution saturated, unsaturated, or supersaturated? Okay? How do you think we would be able to think about this question? Could we go like this? Grams of sodium chloride, because that's what we really want to know, is how many grams of sodium chloride we can dissolve in 50 grams of water. Isn't that true?
Yeah.
So if we go, how many grams of sodium chloride can we dissolve if we have 50 grams of water? What conversion factor do we have?
Put water bottom right.
Okay.
And then we put sodium.
Sodium chloride, grams of sodium chloride. Very good. Do we have any numbers that relate those two together?
We have no.
Well, does it say up here that 39 grams of sodium chloride dissolves in 100 grams of water?
Oh, yes.
So what do I put?
So you have to do 39 divided by 2.
39 over 100. 39 grams of sodium chloride for every 100 grams of water. Right? And now, what will this tell us? It'll tell us how many grams of sodium chloride given only 50 grams of water. So, calculator, 50 divided by 100 times 39, 19.5. 19.5. So that means what? What is 19.5 meaning? What have we found out?
19.5 out of 39.
19.5 grams of sodium chloride can be dissolved in 50 grams of water. 50 grams of water. You see that? So if I have 10 grams in 50 grams of water, is the solution saturated, unsaturated, or supersaturated? How many can I get in there? How many can I get in?
19.5.
Yeah, 19.5. And I only have 10. So is it saturated, unsaturated, or supersaturated, or none of these?
Unsaturated?
That's right. It's unsaturated. To be saturated, I'd need to have 19.5. And if I had more than 19.5 dissolved somehow, I'd be in a supersaturated state. Wonderful job. Good job. Now, we know that you put salt into water and it dissolves. We've seen this before. And I have this video and I've showed it to you a couple times already, but I'm going to show it to us again. When you put salt into water, the salt, sodium chloride, or any salt, any ionic compound, is in this three-dimensional lattice like this. Ionic compounds are in three-dimensional lattices. And we know that the salt dissolves. And this is what's happening, right? The water molecules surround the ions and sweep them off of the big chunk of salt that you just put into solution. And each ion gets entertained, in a way, by many, sometimes hundreds of water molecules. The water molecules gather around each ion, take them away, and this process, which we know as dissolving, it is dissolving, but it's also a new word which we call dissociate, or dissociation. And what the difference between dissolving and dissociating is, if I take a compound A, and let's say it's a solid, and I mix it with, well, we don't usually draw that. Let me try that again. If I take a compound and I put it in some water and make it aqueous, this reaction is called dissolving, all right? But if I take something like sodium chloride and dissolve it into water, because sodium chloride is, well, let's see, is sodium chloride soluble or not? Can you tell me on the periodic table where it says whether or not sodium chloride is soluble in water? Which rule? All right, rule 3, chlorides are soluble. Another rule that tells us that sodium chloride is soluble is rule 1. all compounds that contain group 1A, because sodium is group 1A, right? Okay.
Right.
So yes, sodium chloride will dissolve, but it will also, because it's an ionic compound, it, what we call, dissociates. Whoops, AQ. So the sodium ion itself is now separate from the three-dimensional lattice, floating around with a bunch of water molecules, and that's what that AQ means. The chloride ion also is separate from the three-dimensional lattice and is floating around as with a bunch of water molecules. So this is dissolving, but it's a special kind of dissolving which we call dissociate. Can you say dissociate?
Dissociate.
Very good. Dissociate. And dissociation is important because if I write this now, from now on, for example, if I write Na2CO3AQ, that AQ tells me that it's dissolved in water, and my understanding of the solubility rules helps me realize that sodium is, anything that contains sodium is an aqueous compound. So rule 1 says it's soluble. So that means that when somebody writes that, what they're really saying is you have 2 of these sodium ions that are floating around with water molecules surrounding them. And you have 1 of these carbonate ions that's floating around with water molecules around it. Okay? So we don't have any of this. These are the species that we actually have in solution. Okay? And so that's why it's very important to understand that some compounds are soluble. And when we see aqueous like that, an ionic compound that's soluble, that means that it's floating around as its ions. It's no longer in a three-dimensional lattice like we saw here at the beginning of this video, right? That's as a solid, but when we say aqueous, when it's dissolved in water, then all of the ions are separate from each other. They're dissociated. Okay, very good. That's a good place to start. Congratulations. Bye-bye.